Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 25th, 2026, just about 4 days ago. It introduces a modular three-step recipe that radically simplifies the derivation of high-probability regret bounds for empirical risk minimization. The paper is titled, A Researcher's Guide to Empirical Risk Minimization. And as we'll see later, this framework essentially standardizes the proof process for a wide range of modern machine learning problems. Alright, to make that theoretical framework concrete, Table 1 lists the critical radii for several standard function classes. Recall that this radius, delta n, essentially determines how fast the error drops as the dataset grows. The first row highlights S-sparse linear predictors, showing a rate that depends on the sparsity S. Moving down, we see entries for versus C subgraphs and smooth Sobolev functions, which confirms that this modular recipe recovers the correct, established rates for these diverse settings. So, while the previous table showed the final rates, Table 2 steps back to the raw ingredients, the uniform entropy bounds. These integrals, labeled J infinity or J2, measure a function class's complexity at scale delta. For example, the first row lists the bound for smooth-Holder and Sobolev functions. Moving down, we find the formula for S-sparse linear predictors. The table then concludes with a bound for versus C subgraphs. Essentially, you plug these specific entropy entries into the general fixed-point recipe to derive the convergence rates. Wrapping up, this guide fundamentally streamlines how we analyze learning algorithms. By separating statistical complexity from algebraic proofs, the modular three-step recipe allows researchers to derive sharp guarantees even for complex settings like causal inference or domain adaptation. It essentially provides a standardized blueprint for tackling empirical risk minimization. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.